Welcome to Deep Dive with Phil and Emily. Looks like we're tackling some pretty complex stuff today.
Yeah, gradient descent, derivatives, optimization.
All pulled from Professor Wu's lectures at Northeastern. You ready to break this down?
Absolutely. These concepts are really at the heart of machine learning and data science. It's like trying to find that perfect point,
The sweet spot.
Exactly, the input value that gives you the absolute best possible output.
So, like fine-tuning a machine for, peak performance or something. But where do these derivatives fit in?
Well, imagine a landscape with hills and valleys.
Okay, I'm picturing it.
The derivative of a function, say at a particular point, it tells you the slope of that landscape at that exact spot. It's basically telling you if you're going uphill or downhill.
Okay, so if we're trying to find the lowest point, like the bottom of the valley, the derivative is like our guide.
Exactly. And sometimes you can just calculate the best input value directly. You set the derivative to 0, solve for the unknown variable. That's what's called a closed form solution.
So it's like a direct route. You know exactly where to go.
Think of it like a precise map, leading you straight to the lowest point.
But you're saying this doesn't always work.
Right. In a lot of real-world situations, the functions are just too complex to solve directly.
So it's like our landscape is covered in fog.
Exactly. You can only see a few feet in front of you, and that's where gradient descent comes in.
Okay, because it's more step by step.
Right. It's iterative. It's like navigating that foggy landscape, but taking these small, careful steps downhill.
So you start somewhere random.
Yeah, you start at a random point and use the derivative to figure out, well, which way should I go? Which direction takes me downward?
And then you take a small step in that direction.
Right. And the size of that step, that's determined by what's called the step size.
So step size is like how big of a leap you're taking in the fog.
Exactly. A smaller step size, well, you're moving cautiously, but it might take you a while to reach the bottom. Larger step size, you could get there faster. But, you risk overshooting it.
It's about finding that balance. Can you maybe give us an example to kind of solidify this?
Sure. Let's take a simple function, fx equals x squared.
Okay.
It's a simple curve. We already know the minimum is at x equals 0. But let's say we start with gradient descent at, say, x equals 3.
All right.
The derivative there, it tells us, okay, move left towards 0. We take a step, let's say scaled by a step size of 0.5. So that brings us to x equals 1.5.
Okay, getting closer.
Closer to our target. Then we just calculate a derivative again at this new point, 1.5, and repeat the process.
We just keep going, taking these small calculated steps.
Until we get as close as we can to that minimum value.
Makes sense. But I imagine real-world problems are rarely that simple. What happens when you have, more than one variable to optimize, more than one thing to tweak?
Right. That's where this idea of a gradient comes in. It's like a multidimensional derivative.
Okay.
Instead of just a single slope, you now have a vector pointing in the direction of the steepest descent.
Yeah.
But now it's in a higher dimensional space.
So we've gone from a foggy landscape to a foggy mountain range.
Precisely. Multiple peaks and valleys to navigate.
And we're trying to find the lowest point in all of that.
Right, but the principle's still the same. We use the gradient to figure out what's the best combination of steps to take. How should we adjust each of these variables to get down to that lowest point?
Okay, I think I'm starting to see how this all ties together. So is this how things like linear and polynomial regression work? They use gradient descent to find the best fit for the data?
Absolutely. Linear regression, you're trying to find the best fitting straight line through a set of data points, and you use gradient descent to tweak the parameters of that line.
So shifting and tilting it until it's as close as possible to all those points.
Exactly. You want to minimize the error between the line and the actual data.
And by error, we mean the distance between the line and those data points.
Right. And we use something called mean squared error to actually measure that distance. That's what guides our gradient descent process.
Okay, so what about polynomial regression? Is that similar? But instead of a straight line, we're fitting a curve.
Exactly. We introduce these higher order terms in our equation, things like x squared, x cubed, and so on, allows us to model more complex relationships in the data.
It's like, instead of using a ruler, we're using a flexible curve to try and draw the best fit through those points.
That's a great analogy. And we still rely on gradient descent to fine-tune the parameters of that curve step by step until it aligns as closely as possible with the data. And it's amazing how much you can do with those higher order terms. You can really capture those curves and bends in the data.
But I guess there are trade-offs, right? Like, how do you decide between using linear or polynomial regression? What are the pros and cons of each?
Well, with linear regression, it assumes that the relationship between the variables is, linear. meaning that, a change in one variable leads to a proportional change in the other.
Right.
It's simple, easy to understand, and it often works really well when you've got clear linear trends in your data. But sometimes it's just too simplistic, especially if the data has more complex patterns.
So if the data points are kind of scattered all over the place, linear regression wouldn't be a good choice.
Exactly. That's where polynomial regression can really shine. With those higher order terms, it can capture those curves and bends in the data much better.
But I'm guessing it's not a perfect solution, right?
Well, the downside is that sometimes it can overfit the data,
Overfit.
meaning it learns the specific quirks of the data too well.
So it's like it's memorizing the answers instead of understanding the concept.
That's a great way to put it. And as a result, it might not generalize well to new, unseen data.
Okay, so it's like a trade-off between how well it fits the data and how well it can adapt to new information.
Exactly. It's a classic challenge in machine learning, finding that balance between complexity and generalizability.
Professor Wu also briefly mentions neural networks in his lectures. How do those fit into all of this?
Right. Neural networks are these incredibly powerful models. They can basically approximate any function if you have enough data and the network is complex enough, and they're optimized using gradient descent as well.
But it's probably a lot more complicated.
Oh, it definitely gets more involved. They have way more parameters to tune. But for this deep dive, I think it makes sense to stick with the basics of gradient descent and how it applies to those, simpler regression models.
Makes sense. So let's focus on that for now. I'm curious, how do you know when you've reached the best solution with gradient descent? Like, when do you stop iterating?
That's a great question. There are a few techniques, but one of the most common is to keep an eye on that mean squared error. As gradient descent keeps going, we expect the error to go down with each step, as we're getting closer to that optimal solution.
So we're basically watching that distance between the line or curve, and those data points shrink with each step.
Exactly. And we often actually plot this error over time. You can really see it visually. And when it starts to plateau, or not decrease significantly, that's a good sign that we've reached a pretty good solution.
So it's not necessarily about finding the absolute lowest point, but finding a point where further steps don't really make a difference anymore.
That's a really good observation. And that's actually one of the challenges with gradient descent. It doesn't always guarantee that you'll find that absolute global minimum. But in practice, finding a good local minimum often works pretty well.
So it's more about finding a solution that's, good enough for our purposes.
Often, yes. Especially in real-world scenarios, where the data is noisy and the relationships are super complex. A perfect solution might not even be possible or practical.
Right. Well, this has been super helpful. I feel like I'm finally starting to wrap my head around how this all works.
Good. I'm glad to hear that. It's really a testament to the power of calculus and iterative algorithms, And the applications are just everywhere, from machine learning and AI to finance, engineering, you name it.
Yeah, it really makes you think. And it's like you were saying, it's not just about hardcore machine learning stuff. These optimization problems, they pop up everywhere, right?
Absolutely, they really do. Just think about something as simple as, recommending movies on a streaming service.
Okay.
That's an optimization problem too. They're trying to find the best recommendations for you, the user, to maximize your engagement, keep you watching, keep you happy.
That's pretty cool. So are they using gradient descent to figure out what I want to watch?
Well, they might be using a technique called collaborative filtering, which looks at your viewing history and compares it to millions of other users to find patterns and make predictions about what you might like.
So it's like finding other people who have similar taste in movies?
Exactly. And they might be using gradient descent to optimize the parameters of their recommendation algorithms, constantly tweaking them based on how users respond.
Makes me think about the ethical side of all this.
Yeah.
If these algorithms are always being optimized to maximize engagement, could they end up recommending things that are, maybe not so good for us? Things that are addictive or harmful.
That is a really important consideration. As these techniques become more powerful, we really have to think about the unintended consequences.
Yeah.
Make sure we're using them responsibly and ethically.
It's like we're not just navigating this foggy landscape anymore, right? We're also responsible for shaping the terrain itself, making sure it leads to, a good outcome.
That's a great analogy. And it underscores the importance of having these conversations involving experts from different fields, not just computer science. Ethicists, social scientists, policymakers, it's a team effort.
It really highlights how technology is never neutral. It's a tool, and we decide how it's used.
Well said. I think that's a great place to wrap up. This deep dive has given us a lot to think about, for sure.
Yeah, it definitely has. Thanks for helping us explore this complex but fascinating topic.
My pleasure. And remember, this is just the beginning, really. There's so much more to learn and discover